So let's review some of the pulse methods. And rather than call them potential reversal, they often call them pulse methods, pulse voltammetry. And you can see why. We're taking a step out and a step back, and we can think of that as a potential pulse, and that's what we're doing. The most widely used method in which pulse methods started to be used was in the area of polarography. As I said previously, Horovsky and his school in Czechoslovakia developed polarography. He won the Nobel Prize for it, in fact, one of the first analytical chemists to win a Nobel Prize. And they developed a large body of literature on polarography, and then also that school developed some pulse methods as well. Now, polarography strictly refers to one particular type of experiment, where they take a thick-walled glass tube with a thin capillary. And in that capillary and extending outside it is a drop of mercury. So polarography refers to a mercury droplet electrode pretty much exclusively. So when somebody says they're doing polarography, they mean what they should be saying to you is they're doing it on a mercury electrode. Although occasionally they refer to polarography at non-mercury electrodes, and that's really erroneous. The idea of the experiment, the simple experiment is if I take a reservoir of mercury, hook it up to a flexible tube and my glass capillary. I'm not drawing very well here, but put this in a solution with, say, a reference electrode. Apply a potential to the mercury, and by adjusting the distance of the head pressure on the mercury by, say, against some sort of measuring stick, we can cause the drops to be emitted at a faster rate or a slower rate, and we can cause the drops to fall faster or slower, just so on. And the bottom will get this little mercury pool electrode. Sometimes the mercury pool at the bottom is used as a reference, and first that's what, in fact, they did. Is especially if they did this in a chloride-containing solution, that would actually make sort of an SCE type electrode nice and stable. So drops will either fall dependent on the head pressure of mercury here, or they will fall on the basis of a mechanical dislodging device called drop knocker. There's a little mechanical device that taps the capillary every second or so, something like that, and then that drop will fall off. Drop knocker is actually a more useful method than allowing it to fall naturally, because the natural fall time is affected not only by the head pressure, but also it turns out to be strongly dependent on the potential that you've applied to the electrode surface itself. And surprisingly, initially, is the potential dependence on the drop fall time, but it turns out that by applying a potential to mercury, you're actually affecting the surface potential of the mercury, which is affects the surface tension of the mercury. So it turns out you can actually observe a lot of physical, chemical results by adjusting the potential of the mercury and adjusting the surface tension of the mercury. And we'll talk some about that a little bit later. The reason polarography is very desirable as far as electrochemical method and also as an analytical method is that every time that drop falls, we get a nice, fresh, clean drop of mercury. So the electrode surface is clean and fresh, doesn't need to be renewed at any point. It's renewed every time that drop falls, maybe once a second. And not only that, because that drop is always growing, the surface is continually being renewed, even during the course of the growth of the mercury. The other advantage is that the overpotential for proton reduction is very large on mercury, so we can do experiments in acid solution without any trouble. which would cause trouble with, say, platinum electrode. So in acids, where a lot of metal ions are stable, we can do polarography on those metal ions. Whereas in non-acid solutions, many metal ions are not stable, and so an electrode like platinum would not be as useful. On the other hand, even though the overpotential for a proton reduction is very large, other materials has a very rapid rate constant, so many rate reductions are very rapid on mercury, more so than other species. The surface is also very smooth. You don't have to worry about polishing it. The drop fall also, in addition to forming a new clean electrode, also forms a new concentration gradient at the electrode surface. Every time that drop falls, you get a little bit of stirring of the solution, and it regenerates the concentrations at the electrode surface. And so it restarts the experiment from the beginning, essentially. Well, in addition to the advantages, there's some significant disadvantages, which weren't always apparent at the start of when the people started using it. First of all, it uses mercury. It uses a lot of mercury, and it uses it in a way that often allows it to be spilled and contaminate your laboratories. So some of these old polarography laboratories probably are very hazardous places to be in because of the amount of mercury that's floating around. So that's lost. It's lost its luster for that reason. The other problem is that on a polarography, the anodic processes are limited. You can't really do oxidations on mercury to any significant degree because mercury itself is easily oxidized. So the electrode becomes oxidized, particularly in chloride-containing solutions. It's easy to oxidize to form mercury chloride, and so on. Third reason is the theory is very messy. It's an expanding drop. You've got a new concentration. You've stirred the solution a little bit, so it continues to be stirred even when the drop is growing. To accurately do a theory for mercury drop electrodes is very difficult. And so the theory has been somewhat semi-empirical, although some pretty good rigorous theories have been developed, but they don't include things like heterogeneous kinetics and homogeneous kinetics, except in a semi-empirical way. So the advantage of polarography as a dropping mercury electrode has been mainly for analysis. There is, however, a contender called a static mercury drop electrode, which has some advantages of the dropping mercury electrode, but some advantages that are not so apparent. Dropping mercury electrode is here. Static mercury drop electrode. Rather than using a capillary tube with mercury hanging off it, it actually uses a little support. Often it's a little platinum wire. Platinum and mercury will amalgamate slightly and have enough adhesion so that you can actually stick a little mercury drop on the end of that platinum. You take a little cup and you can poke it on there, or you can use a little device, a little micro syringe to extrude a small drop of mercury. In that case, there's no problem with the mercury drop expanding during the course of the experiment. There's no problem with having it drop off at some particular time. Disadvantages, though, it gets dirty now, and it still is using mercury, still has the problem with anodic processes. Finally, dropping mercury electrode, that capillary has to be scrupulously clean. It's really difficult to clean it, and if it's not clean, the drops don't work right, and you get all kinds of crazy behavior. And so it's kind of a pain to do polarography, although in skilled hands, it's a very useful method. For all these reasons, polarography is falling out of favor for many analytical applications. And so we're replacing it with techniques that we'll call voltammetry, which, except for the type of electrode material, are basically the same techniques. Voltammetry was originally used for solid electrode work. So rather than a liquid electrode, mercury electrode, we use a solid electrode like platinum or gold or carbon. And the experiments that we do on there would be called voltammetry rather than polarography. It seems a little arcane to have two words for the same basic experiment, but that's the way it goes. So we're going to talk about voltammetry and not polarography. The book talks about polarography because when the book was written, which was over 20 years ago now, people still did a lot of polarography. People don't do so much polarography now, and so we're not going to talk about it. If you do use it, the theory isn't that tricky. You can read it. To use it in the analytical sense, you can read it and understand it pretty quickly. We're going to talk about voltammetry, and voltammetry, particularly when it's applied to pulse methods. A lot of the stuff was originally developed for polarography and has been just applied to voltammetry methods. The big problem with voltammetry over polarography is voltammetry really has trouble with surfaces not being as clean as mercury, and that contamination process is very critical. The pulse voltammetry that started out and was a polarographic method was called normal pulse polarography, or normal pulse voltammetry. Normal pulse voltammetry is a method in which you start at some initial point. We'll call it E sub B for potential, and we apply a series of pulses that have an increasing step size. So what we do is we start out, we have a little tiny step, and then we wait some amount of time, and then we have a little bit higher step, and we wait some amount of time, and then we have a little bit higher step, and then we wait some amount of time, and then we have a little higher step, and so on. And we keep doing that for over and over and over again. And these little pulses are about 50 milliseconds, although it can be a little shorter, it can be a little longer. And this time in between the pulses is can be 2 seconds, can be shorter, longer, depends a little bit on the experiment. So in other words, we're waiting quite a bit of time with respect to the time that we're actually pulsing the material. The increment of additional potential for each step up is about 5 to 20 millivolts. So every time we do a little increment, we're incrementing it, say 5 millivolts, 20 millivolts, probably 20 millivolts is more typical. And what we do then is we are doing, does that red show up good on the screen or not? Can you see it okay? Is it better than the black or worse than the black? Okay. The pen is better, so it's easier to draw with it. Basically, the idea is with normal pulse polarography, it's like our sampled current chronoamperometry, exactly equal to our sample current chronoamperometry. What we're doing is we're just doing a series of steps where we're stepping and stepping and stepping back, and we're only really considering the forward current. And what we're doing here is starting from our base potential, we're stepping up, stepping back down again, and we get a Faradaic current. And what we do is we sample at tau prime. And we sample just before we step back. And the advantage of that is there's no real advantage to the fact that we're sampling right at tau prime. We don't want to sample before tau prime, because if we were going to sample before, we would just as soon step back at that particular time. So we're always going to be sampling right at the end of our drop, or end of our pulse. Maybe if we were sampling here, we would step back at that point. The advantage of sampling at a later time is that, remember, there's charging current also involved in the process. And so there's a Faradaic current, And practically, we have some charging current. We haven't talked about charging current in the theory, but in experiments, we have to worry about it. And remember, because of the way the charging current is, it's going to decay much more rapidly than the Faradaic current. So by holding off on our result, we can sample later in the drop, the charging current amount is less. On the other hand, which means when it's less, it means that we're going to have more sensitivity. On the other hand, if we sampled earlier in the pulse, we would get more current flow. And so it's a trade-off between the charging current that we don't measure later in the drop or the more current that we can measure if we sample earlier in the pulse. All right, we sample there, and if for polarography, we'd knock all the drop off, or for voltammetry, we would just continue on. Well, the current under these conditions is, and what you'll notice is that almost in every case, we've assumed essentially reversible behavior for the electrochemical behavior for our analytical results. And that's sometimes good and bad. The assumption makes it easier to do the calculation, but the bad thing is that it's often not the case that we've got irreversible behavior, so our theory may not fit our experiment as well as we'd like. All right. So what we're seeing there for diffusion coefficient, and so as we make this distance time shorter, more current flows. We should have more sensitivity, but we've got this charging current problem to worry about. We have to wait that long time between the samples to reestablish equilibrium. Every time we do a step back and forth, we're perturbing the concentration profiles near the electrode surface, and we have to maintain, re-equilibrate the system, and that usually means that we're going to have to wait usually 10 to 100 times the T minus T prime, or tau minus tau prime. And so what you get out of this result is this sample current voltammogram. And depending on, again, how many points you've got, how often you think. It's a pretty slow method, as you might imagine, because we have to wait 2 seconds or so between every point. It's going to take a significant amount of time to generate that curve. Not a huge amount of time, but a minute or more. 2 minutes, 3 minutes would not be atypical. You do get pretty good results with the sensitivity, not great, but for a simple method that it is, 10 to the minus 6 to 10 to the minus 7th molar type of sensitivity that you're going to be seeing. One of the other advantages I didn't mention is the pulse polarography type methods is that they're very amenable to computer control because the computer can apply good timing pulses and apply good times between pulses. We can have good computer control of our experiment, and so a lot of pulse polarography drove out of the sort of the novelty of having a computer running the experiment, and how could we develop a new method that would be specifically suited for a computer control. And so a lot of these started in the 70s and 80s when people were using computers a lot for controlling electrochemical experiments. One thing that has really revived pulse polarography's and voltammetry's fortune is the introduction of microelectrodes. Because unlike the larger electrodes, this time between pulses no longer has to be so long. If you remember, because of the rapid diffusion times and the rapid convergent diffusion, the efficient convergent diffusion, those re-equilibrium times can be much shorter, 100 milliseconds or shorter, and so the time to do the experiment can now be much, much faster. And so that's a big advantage. If you have to do an experiment and it takes 20 seconds rather than 20 minutes, it's something that you're really going to think about. All right, well, one other advantage, one other experiment that helps a little bit to discriminate against this charging current process is called differential pulse voltammetry. And the experiment is slightly different. In fact, people have different names for what we're doing here. But the idea is something like this. And rather than stepping back to the baseline, we're stepping back to some new potential, and we go forward maybe, what do I get there? That might be a half a second to 2 seconds. This again would be a short time. 5 to 100 milliseconds would be a typical amount of time. And this step up and back would be 20 to 100 millivolts. And that again would be, 10 to 100 millivolts up on the thing. Now what you're doing essentially is you're using the increasing baseline as setting an equilibrium conditions. Because this is a fairly long time period between pulses, we can assume that the electrode response is at equilibrium. We can assume Nernstian conditions at that case. A lot of times we have to worry about that, but because we've got a long time frame between the pulses, the system can achieve Nernstian type equilibrium, hopefully, under those conditions. And the idea is that we can step from the base to the step potential and then back, and then measure the difference in current between those 2 points, between the time tau and tau prime. And our current would be measured at that same point. And this would be E base down here. So every time we do a step out and back, we measure the current as a function of tau, tau prime. We plot that versus the base potential. Essentially what we're going to have is a derivative of the normal pulse voltammetric curve. When we do that, and we get a delta current. It's not strictly a delta, but pretty close. And we get this nice Gaussian shaped curve where E is equal to E max, or E is equal to, or E max is equal to the center of that curve. E max should be equal to E1/2 minus delta E over 2, where delta E would be this distance here. Okay, so the larger the delta E is, the shifted away from E1/2 would be E max. And so E1/2 would be the half wave potential of the wave that we would get under, say, a normal pulse voltammetry conditions. So the larger we make the steps, the more current we get out of it. The shorter we make the steps, the smaller amount of current we get out of it. So the delta I max at the peak at the maximum amount is NFA D0 to the 1/2 bulk concentration. Okay, and then we get expression like this. And this, again, is for a reversible system. This is the appropriate theory. And sigma is equal to an exponential function. That's a little bit complicated theory. Pretty much you don't worry too much about that. You just do a calibration curve, and then you figure out what the lambda max is or delta max is, and do it from there. I guess we're running out of tape, so we'll do a stop. We'll stop here and take a little break.